Testing, testing. Okay, I think that's coming through. All right, so we're going to do the Chapter 6 test on special relativity. I've got my exam equation sheet here. Let's have a look. I've got my notebook, which I'm going to be writing my answers into. And we've got the test, so let's give this a go. Off screen, I've got some sample answers that I'll refer to check that I'm not making too many errors as I go through this. But I like to do these off the cuff all the same. All right, so let's get started. Question 1. Consider two vehicles some distance apart and moving towards each other, directly towards each other. Each vehicle is traveling exactly 20 meters per second relative to the ground. All right. At what speed would each vehicle see the other one travel? Okay, so we're moving far too slowly to really take effect of any relativistic factors. So essentially, you've got one car. You want to draw a car. It's going this way. The other one's going the other way. And both are going 20 in opposite directions. All right. So basically, the relative speed of each other. If this one was, if you think about yourself sitting in this one stationary, then the ground's moving 20 meters per second past you, and this car's moving 20 meters per second in that direction even faster. So really what we have is 20 meters per second plus 20 meters per second equals 40 meters per second. That's it. Okay. As the two velocities approach each other, a passenger in each car shines a torch towards the other car. At what speed does each car's occupant see the light from the other's torch travel? All right, so effectively, this is the speed of light. And I'll just read the description as given here. Einstein's second postulate states that the speed of light will be the same no matter the motion of the light source of the observer. So you don't get the speed of light plus whatever speed they're traveling at relative to the other observer. No, the speed of light is the speed of light is the speed of light. And that's one of the effects of relativity. So that's what we've got in the theory. Question 2. Galilean relativity states there's no absolute velocity, rather all velocities are relative. Use an example, explain what this means. Your example should use numerical values. Okay. Well, we really just saw one essentially with this example here, but okay, I'd like to use a different example. I'm not going to use the one that's given in my solution, so I'll just consider this. I like, because I talk about projectile motion, I use this particular example of relativity to to consider and explain components in projectile motion. So say, for example, you're in a train or some sort of train card or something to that effect, and you've got a little ball in your hand, and you decide, okay, I'm going to throw this up. So say, for example, you throw that up at 10 meters per second. But then the train carriage is moving at 5 meters per second. Okay. All right. So in your reference frame, that just moves up and down. Okay. Whereas, so that's initial velocity, vertical velocity up 10 meters per second. I probably should use an example that's just in one direction, but for this particular instance, this is what I've done in the past. Okay, now, so the train car's moving past. So for you, it's just gone up and down. So you go and you thereby catch it as only here. Okay, in its car. Okay, but so we got observer over here in a different reference frame. Okay, so she has been watching this train go past. All right, and she's been standing still. So she observes that this has been moving faster. So she's observed basically the vector sum. What she observes is the vector sum of the vertical motion and the horizontal motion as a vector sum. So at least initially, what she's observing is you have like essentially 10 meters per second up plus 5 meters per second this way. She observes that velocity here. So that's the kind of velocity total. That's what she observes. All right. So that is an example of that. All right, so I've kind of talked it through. I didn't write that out. You can use a simple example just by talking about. So the example that's given in these notes, a person standing by the road is measured car traveling at 50 kilometers per hour, but a cyclist traveling at 15 kilometers per hour in the same direction. The car appeared to be traveling 35 kilometers per hour relative to the cyclist. So they imagine the car overtaking the cyclist, but relative to the cyclist is traveling at 35 kilometers per hour past them. Right. That's their example. So this part, how does special relativity contrast the Galilean relativity in respect to velocity? In special relativity, speed of light is the same in all frames of reference, but according to Galilean relativity, the speed should vary with the frames of reference. All right. So two spaceships traveling. Let's move on to this one. Two spaceships are traveling towards the right, past Earth, side by side, the same high velocity. The captain of the first spacecraft sends a radio signal, hence is traveling at sea, the radio signal, to the captain of the second spacecraft. The captain of the second spacecraft then sends a signal. The situation is illustrated below. So, okay. The captains of the spacecraft record the time for the signal to pass between them as less than what an observer in the spacecraft in the command center of the Earth records. With an aid of a labeled diagram and supporting description displaying this apparent contradiction. All right. So, all right. So, all right. So what I've seen here, I'll just draw these. Okay. So we'll call that number, that's number 1. All right. Number 2. And number 1 again. All right. So when you send a radio signal, you send it out in essentially all directions, but we'll draw just the lines in terms of when it would meet the receivers. It will send from this antenna and meet the receivers of the radio signal. So when Spaceship 1 sends a signal, it goes in all directions, but it gets received wherever it finds Spaceship 2, which is over here. Okay, so there you go. And then Spaceship 2 sends a return signal, but the time it actually travels through space and Spaceship 1's been traveling across, it gets received over here. So this is Spaceship 1 again. So that's what we're looking at, because these are all moving to the right. Now I'll draw the Earth over here, observing all this. Okay. So the signal from the perspective of the ship's captains travels 2D. So the time for the signal to be sent. So essentially, as far as the ships go, they look like this picture here. So they've been traveling. They've been both traveling to the right. So they've both been traveling, and they appear to be on top of each other from their reference frames anyway, because they're both traveling at the same relative speed. But as the signal was sent from one to the other, this one would have, as you send a signal from 1 to 2, Spaceship 2 will be further to the right by the time that signal has arrived, and that's what the Earth observes. So this is what the Earth observes. So Earth observes the signal from 1 going to 2 over here, and then the return signal will be going down over here, because these are all moving relative to the Earth. So, the signal perspective of the ship's captain is traveling 2D from the time signal has been sent, the return signal is given by. Okay, so the idea in relative terms, okay, so the spaceships will be sending this distance, whereas the Earth observes it as this, then that. So the time of the signal, okay, so this is distance A. The time relative to the, I'm not seeing that properly, the time relative to the spacecraft is 2D, so up and back, divided by C. Okay, from the Earth's, so this is for, this is in the reference frame of the ships. I'll call that the ship's frame. Okay. Now, I'll get a bit more space. There we go. All right. So the Earth observes this. So this length is longer than that, and this length is longer than that going down. So that's what the Earth observes. From the Earth's observer's frame of reference, because the ships are moving by the time of the signal from ship 1, which is ship 2, the distance for the light to travel from ship 1 to ship 2 is greater than d, similarly for the return signal. If we let x be the distance from the Earth observer's perspective, then the time of the Earth observer will be, okay, so we call that distance there, that's x and that's x. Okay. Then the time from the Earth's observer's frame, so TE, is 2x over c, with x being larger than d. Okay. So that's what's happening there. So we've gone and explained this apparent contradiction. They don't need to put in the Lorentz figures to do that at this stage. Okay. All right. Question 4. The time t0 and length l0 are referred to proper time and proper length. Using examples to explain what is meant by proper time and proper length. Proper length is measured at rest between 2 points. If the distance between 2 points, whose positions are measured by an observer at rest with respect to the 2 points. So, for example, the proper length in what we just did before. Okay, so the spacecrafts being in the same reference for each other could measure their distance apart. They're moving together with the same velocity. So their proper length would be d. And proper time is essentially the signal between the two of them being sent back and forth. Okay. So yeah, when it's proper, it's within the same reference frame, inertial reference frame, I should say. Okay. One of the evidences to support Einstein's special theory of relativity is observation of half-life muons, which travel at speeds close to the speed of light. If the rest half-life of muon is 2.2 times 10 to the minus 6 seconds, what is the half-life of muon traveling at 0.9 c? Okay, so we're going to work out, all right, so from our list of formulas, T is equal to it's T naught times by the Lorentz factor. Okay, all right, and that is on our formula sheet right here. Lorentz factor is there. Okay, that one. Okay, time dilation T equals T naught Lorentz factor, and Lorentz factor is here. Okay, so let's go use that. Get back to my notepad. All right, everyone, let's bring that back up again so I can see more page. It's a little bit easier. All right, so we're going to express it like this. Over square root of 1 take v squared v c squared. Okay. And we're going to substitute in some values for that. All right, so the proper time is 2.2 times 10 to the minus 6. And okay, square root of 1 minus 0.9. Now I'm going to, let's actually put that in parentheses, over c squared. Okay. All right. One take. Now there'll be 0.9 squared, c squared over c squared, and you can cancel the c squared, so we don't even have to substitute the speed of light here. All right, and let's simplify that. So back down here. Okay, so 2.2 times 10 to the 6. Oops, yeah, broke my pencil. All right, salvageable. So on that last. Okay. Okay. Not broke it, but it's held in place. All right. All right. So that's 1 take 0.81 on there. All right. So let's punch that in the calculator. This is a good point to put in the calculator and work that out. All right. 2.2, and that's e minus 6. It's a short amount of time. What we're demonstrating here is while the half-life of muons means that half of them would decay within this fraction of a second, they will actually last a bit longer than that, or at least half of them will be last longer than that in our inertial reference frame. Okay, 0.81. Okay. All right. So then we have a longer time. Through some figures, 5.05, 10 to the negative 6 seconds. Okay. Just double check. All right, then you round that up. Actually, you rounded, that was 4.7 in the calculator. To two different figures, it would be 5.0 times 10 to the minus 6. I have a habit of holding on to an extra significant figure. All right. Okay, part B. If an observer was able to travel with a muon to measure its half-life, what would be its measured half-life? Now, again, this is essentially the same sort of conceptual question as what they're trying to get you out to explain in part in question 4. So if you are in the same inertial reference frame as the muon, you will observe the proper time. Okay, so then this would be T naught, which is, so part B, question 5. So on question 5, I actually put that in. All right, so T naught will be 2.2 times 10 to the 6, negative 6, I should say, seconds. Yeah. So that's what it would be. Yeah, and the justification, the second mark would be, this is because the observer will be traveling at the same speed as the muon. The muon would appear to be at rest because you're in the same inertial reference frame. All right. As the muon travels through the atmosphere, they measure a height, the hill of 200 meters. What is the height of the hill measured by the scientists by the Earth? Okay. So the scientists on the Earth would be the ones that are measuring the proper length. So that's actually the unknown variable here. All right. So the muon measures, if the muon was able to measure, the height being 200 meters. So we're actually solving for the other case. So L naught will be, I should say, actually, let's just go with the formula. L equals L naught Lorentz factor. Okay. So then L equals L naught divided by square root of 1 minus v squared c over c squared. Okay, well, that's times that across. So then L naught equals length times this funny creature. Okay, there we go. So we've rearranged that. So, okay, let's do that. All right, L naught equals 200 times, well, this all ended up being 1 take the square root of 0.81. So let's do it in my calculator. Okay. No, that's not right. Let's see, did I get that right? Okay, let's have a look. Okay, what have I done rearranging that wrong? L equals L naught times. Yeah, that was it. That was it, times. And then that would actually be a divide. My bad, I got this backwards. The idea is we're actually, in this case, we're meant to getting something smaller because when you the observer that is observing something moving fast will see contraction, whereas if you reverse that story, it would be the actual length would be longer than the contraction. That was the error that I'm looking at here. So let's fix that up. Let's change it into a divide, and we should be okay. That's what we're looking for. Yeah, so 485. I'm going to round it off, do some figures. So that's going to be 460 meters. There we go. All right. Given the distance that the muons need to travel and their half-life, Newtonian physics predicts that muons created in the atmosphere should not be able to reach the Earth's surface. Which is not observed by not what is observed by scientists. They observe they do. Okay. Explain how it's possible for muons to strike the Earth even with their short half-lives and long distance of travel. So I'll just read out this description. Muons travel at very high speeds. At these speeds, relative physical effects are significant. According to the muons frame of reference, the distance through which they travel to reach the Earth is contracted by a factor of gamma, Lorentz factor. According to the scientist's frame of reference, the time for muons' half-life is dilated by a factor of Lorentz factor, and so a significant number of muons live long enough to make the journey. That is the 4 marks in there. Okay. Question 6. A comet is traveling far away from the Earth, at the speed of 0.18 of the speed of light. A space probe has been sent to observe the comet, measures a long axis to be 32 kilometers. When the long axis is traveling away from the Earth, what length does the comet appear from the Earth? All right. All right. So from the Earth, so percent comet it measures this long axis within that. All right, so we're going to be taking that this is actually the proper length because the space probe is moving along with it. So again, we're going to work out the contracted length. All right, so let's work this out. 1 minus v squared on c squared. All right, so L equals now, you don't have to necessarily, because this is L and L, and this is actually a little unitless value, you could actually substitute in. You don't have to convert this to meters necessarily. So I'm going to keep this as 3.2, and just remember I'm dealing with kilometers. Because this essentially, as far as the units go, cancel out. So these are the two speeds, they'll cancel out in this equation. Okay. So 0.818 squared c squared on c squareds cancel out. Okay, so we equal 32 times the square root of 1 take 0.18 squared. Like that. Okay. 3.2 times. Okay. 1 minus 0.18 squared. All right. Yep. 3.15. All right. The comet is rotating on its axis such that the long axis at times vertical is at times vertical with the Earth. What length will the comet appear to have to an Earth observer when it's in this position? Now it would have this. It would have the same length, and you don't have to explain this one, but I will anyway because only one mark. Okay. All right. So if you have a body that's moving at something like relativistic speed, and you've got so when the observer looks at it, basically, like if I say that this is, I'll call that Ly, and that's Lx. Now, Lx does contract, so you have Lx times by Lorentz factor. Ly does not. This is not. It's not moving up and away. So it's just moving from left to right. So Ly equals L naught y because, well, basically because this would actually be 0 in terms of that direction. That's, well, it's, sorry, not 0. It'll be 1. It'll be because in that particular direction. Well, basically. V squared is so much smaller than, or it is 0 effectively, even if it's just slightly drifting up. Essentially, there'll be the square root of 1, which is 1, and then that goes to 1, and then that's the same thing. Yeah, so Ly, this is not contracting, so if it's moving very, very fast, it would appear very, very thin, according to this this reference person. Okay, but it will still appear very tall. Yeah, the height will not change. All right, moving on. Question 7. A probe has been sent to a planet outside our solar system from Earth. The planet is measured 40 light years away. At what velocity does the probe need to travel to give a distance of 20 light years? Okay. All right. So the idea is let's get our head around this. Let's just write down this stuff. Okay. So proper length is 40 Ly, and velocity. Okay. Well, what velocity is the probe needs to travel? So we're actually solving for v. V is the unknown. Okay. And L equals 20 light years. So you probably, as I mentioned in the previous question, the beautiful thing about the Lorentz factor is it's actually unitless. So we don't have to convert these to meters. So light years is the distance is the measure of distance, is how far light travels in a year. So you can think, okay, speed of light times by 1 year times 365.25 days times by, and so on and so forth until we get to seconds. You don't have to do any of that. Let's just go back to this. So let's just start here. Times by Lorentz factor. Okay. Well, 40 equals 20. I'll just reverse that. So really, initially, we're solving for Lorentz. Okay, that's equal to 1/2. Because basically, if you wrote the light years in here in the algebra, you would cancel them out. So really, this is unitless and this is unitless. Okay, but then let's get this out. Okay, 1 on square root of 1 minus v squared on c squared equals 1 on 2. Okay, so reciprocal of those, square root 1 minus v squared on c squared equals 2. Square both sides. 1 minus v squared on c squared equals 4. And we'll bring this across over here. Okay, let me just bring this up. There we go, got some space. All right, so is that okay? I'm just worried I'm getting issues with negatives here. Why have I got this backwards? I've got ahead of myself. Issue was with, I had this, sorry, I had this. That's why I should have looked at my notes first, because I had this written backwards. Okay, let's just scrap that. All right. So really what it is, okay, let's just go from here. All right, so 20 equals. No, that's fine. L equals L naught. Okay, let's just go from this one. L equals L naught square root of 1 minus v squared on c squared. There we go. All right. So 20 equals 40. How about this? Okay. And all right, divide that across. We've got 1/2 equals 1 minus v squared on c squared. Okay, square that. 1/4 equals 1 minus v squared on c squared. All right, I'm going to bring that across and bring this across. So basically, v squared on c squared. So I brought that across. I added v squared plus c squared on both sides, and I'm going to subtract by 1/4 on both sides. So 1 take a quarter is 3/4. There we go. Then I can take the square root of both sides. V on c equals square root 3 on 2. And if you want to break into decimals, it doesn't really matter at this point. We're going to round things off anyway. Times by c. Velocity equals square root of 3 on 2c. And I'm going to grab my calculator and I'm going to work out what that actually is. Okay. Sorry. I'm going to work out what factor of c it is, because that's really all I need. Okay. That is, v is approximately 0.866c, or 0.87c. All right, that's the correct answer. Apologies for the mix-up. All right. So moving on, question 8. Which of the following describes an internal frame of reference? Internal frames accelerate at a constant rate. Inertial frames accelerate at a constant rate. Inertial frames change velocity at a constant rate. Inertial frames move at a constant velocity. Inertial frames do not move relative to one another. Constant velocity. Dealing with accelerated things moving at the speed of light is far more complicated. So moving at constant velocity, that's all we can really do for that one. So the correct answer is 8. Question 8 is C. Okay. The ladder paradox is a famous thought experiment in relativity. The experiment tells of a ladder that, while it rests within a garage, it is too long to fit into the garage so that the doors cannot be closed. This scenario is witnessed by an observer on the ground and the same inertial frame as the garage. The ladder is then made to approach the garage at relatively speed. It travels horizontally. All right, so let's just draw this. Okay, so we've got that. Okay. So I imagine, okay, we've got a garage door. I'll just draw this kind of like, okay, this garage door. Okay, and then this is kind of garage in here. I'm just got a roof and whatnot. So we're gonna try to get something into this garage. All right, and all right. So ladder is too long to fit into the garage. The doors can be closed. All right, so we're gonna. Here's our ladder. It is too long. So too much. So we're going to just move it in really, really quickly and get it to fit in. Okay, the ladder is made to approach the garage at relative physics speeds. It travels horizontally parallel to the ground, and this time the observer frame of reference witnessed the ladder fit momentarily, at least, completely inside the garage. So it's moving here, and the witness observes that it is shorter than what it was before. Okay. The ladder is now traveling at relative physics speeds. So to explain part A, the ladder is now traveling at relative physics speeds. The observer in the frame of reference of the garage will see the length of the ladder is contracted. The ladder is contracted equal to the Lorentz factor. The contraction is great enough for the ladder to fit inside the garage. This is not a practical application because it would only be inside the garage for a fraction of a second and then would break through the back of the garage. So, yeah. A second observer riding on top of the ladder claims the ladder does not fit inside the garage even when traveling at relative physics speeds. Is this observer correct? Justify your answer. Now we have this with the twin paradox, where both twins would observe the other twin having aged relative to their own reference frame until they kind of met up again, and then we had to explain that section. This is the same kind of principle. In fact, what the observer riding, so now we have a person riding on this ladder, go, yeehaw, that's very fast. They would actually observe, it would be even worse because they would observe the garage contracting, I believe. Okay. So I'm just reading from my notes. Yes, the second observer is correct. In his frame of reference, the garage is too short to house the ladder completely. The garage will see the front of the ladder begin to emerge from the garage before the other end has entered the garage. From this observer, the length of the garage has contracted. Yes, that's correct. So that length, the garage has contracted. So it is far too short to house the ladder completely. So for part C, how does this ladder paradox relate to the concept of simultaneity? Events that are simultaneous in one frame of reference need not be simultaneous in another. From the observer in the frame of reference, the garage, the event of the ends of the ladder meeting the ends of the garage were simultaneous in his event. Yeah. From the observer of the ladder, the event at the front ladder leaving the front of the garage occurred before the event of the back end of the ladder entering the back of the garage. Okay, and that is that's the end of that test. So see how you went with that one.